So, hello everyone. Today we are going to be reviewing the paper with the title Symmetry-protected self-correcting quantum memories. To give you a brief overview, we'll start off with an introduction and we'll first go through the background required to understand the major topics, namely the basics of self-correcting quantum memories and the topological phases with symmetry. And we'll also look at how symmetry constraints ensure self-correcting quantum memories. Then we'll look at the first model that is studied in the paper, which is the RBH model. We'll look at its bulk and boundary properties and we'll look at the cubic RBH code. Then we'll move on to the second model that is studied in the paper, which is the gauge color code. Alright, so quantum algorithmic codes can be used to protect information in a noisy quantum computer, and it's theoretically possible for these codes to be self-correcting as well. So in seeking models for self-correction, inspiration has been drawn from recent advances in our understanding of topologically ordered spin lattices. Now, if global symmetry is imposed on a model, the system can develop new quantum phases, and this has led to new types of phases such as SPT and SET phases, which we'll be seeing soon. In this paper, it is shown that such phases can support self-correcting quantum memory, so SEQMs in 3 dimensions. Two examples of such models are also studied, which are the RBH model and the gauge color code, which we'll be seeing soon. Now let's look at a brief background on SEQMs, or self-correcting quantum memories. The requirements of a SEQM has been formalized by the so-called Caltech rules. That is, an SEQM in d spatial dimensions is a quantum many-body spin system with the following properties. The Hilbert space consists of a finite density of finite dimensional spins. The Hamiltonian has local terms with bounded strength and range, such that each spin is in the support of only a constant number of terms. The ground space of H is degenerate, such that a qubit can be encoded in the ground space, and this ground space is also stable to perturbations. And finally, most importantly, the lifetime of the stored information after coupling the system to a thermal bath must go without bound in the system size. And we'll be showing that it goes exponentially with the system size. Now, the central question for candidate SEQM is how long the encoded information can undergo thermal evolution, that is, be exposed to the surrounding, while still being recoverable. The standard approach to modeling thermalization is to couple the system to a thermal bosonic bath. And yeah, thermalization is modeled by this equation over here, where H4 is the Hamiltonian of the whole universe, system plus surrounding. H6 is the Hamiltonian of the system, H bar is the Hamiltonian of the bath, and the remaining are the interaction terms, where S alpha and B alpha are the local operators acting on the system and the bath side, and lambda is a coupling constant, which is usually less than 1. Now, assume that the state is initialized as rho naught. After some time, it evolves to rho t. We wish to recover rho 0 from rho t, which can be done by error correction. And it consists of 2 steps. Firstly, a sequence of measurements is performed on the noisy state to obtain an error syndrome. Then a recovery map is performed that depends on the syndrome. The net action of the syndrome measurement and the recovery map can be condensed into a single map, that is phi EC. And for a fixed error rate epsilon, we can define the memory time tau mem as the maximum time for which this inequality over here, which is the norm of the phi EC vector from rho t to rho 0, is satisfied. Is less than epsilon is satisfied. This gives us a measure of the memory lifetime of an SEQ, which ideally should go with system size. And we can see that, like, if you solve this equation, it will lead to an exponential growth with system size for tau mem. Now let's look briefly about topological phases with symmetry. Quantum phases of matter are characterized by their ground state properties. When symmetry is at play, the classification becomes richer, as all Hamiltonians in the family must respect symmetry. In particular, it's possible that two Hamiltonians that are equivalent in the absence of symmetry become inequivalent in the presence of the symmetry. This leads to the notion of SPT and SET phases. Now we assume that a system has symmetry described by a group G, a unitary representation S. And consider a lattice lambda in d dimensions with a capital D dimensional spin placed at each side, I belonging to lambda, each side of the lattice. We say two gapped Hamiltonians with symmetry S of G belong to the same phase if there exists a continuous path of gapped local Hamiltonians from H0 to H1 that all obeys the symmetry S of G. Now for SPT and SET ordered systems, one commonly considers global symmetries that act via an onsite fashion on the underlying degrees of freedom. That can be expressed by this following equation, where U of G is a local side independent representation of G. Now let's take a look at SPT phases. These are defined as the class of symmetric Hamiltonians which are equivalent under local symmetric transformations. They do not close the gap and are not in the same class as the trivial phase. Here in this slide you can see the difference between a non-trivial phase and a trivial phase. So basically SPT phases are not in the same class as the trivial phase when symmetry is enforced. And the SET phases are defined as the Hamiltonian that is distinct from the trivial phase even without any symmetry construct. And these 2D SET phases appear naturally on the boundary of 3D SPD phases. Now, the relationship between self-correction and thermal stability or topological order is complex. While we do not yet have a general result connecting these two, we can explore the connection between these two further through the example of the RBH model that we'll be seeing soon. Now let's take a brief look at higher form symmetries. We'll be making use of these higher form symmetries for the future topics. A Q-form symmetry is given by a symmetry operator associated with every closed codimension Q submanifold of the lattice lambda. And the symmetry operators are given by this equation over here. You can see that it's similar to the equation that we had for describing the symmetry operators of the SPT and SAT ordered systems. And of particular interest for us in this paper will be one-form symmetries in 3D systems, which are the next weakest generalization of the conventional global onsite symmetry. Now let's look at the first model that is studied in the paper, which is the RBH model. It's a 3D self-correcting SPT ordered system under one-form symmetry. Let's first look at the bulk properties of the RBH model. Now consider a 3D cubic lattice L and label the set of all vertices, edges, faces and volumes of L by V, E, F and Q respectively. For now we ignore any boundary conditions. We place a qubit on every face and on every edge. Similarly, we label the interior vertices, edges, faces and volumes by V0, E0, F0, Q0, and L0 is the collection of all interior sets inside the lattice. The bulk Hamiltonian is a sum of commuting cluster terms given by this equation, where each cluster term, Kf or Ke, is a 5-body operator given by these equations here. Now these cluster terms are depicted in figure 4. As you can see in figure 4b, we can see the bulk cluster term Kf. Now all excitations in the bulk can be created by products of poly Z operators applied to the ground state. These excitations can be locally created on any side by flipping a spin, and they have no interactions with each other, and the energy cost is proportional to the number of flipped spins. Now the model HL0 has a Z2 to 1 form symmetry consisting of operators on closed two-dimensional surfaces on each of the primal and dual sublattices. A quick side note here, primal here means face and dual means edge. So primal and dual sublattices are the face and edge sublattices for each of the closed two-dimensional surfaces on the lattice. In particular, a generating set is given by the vertex and cube operators given in this equation here for SQ and SV. And these operators are depicted in figure 5. As you can see in figure 5b, we have the primal generator SQ. Taking products of these operators gives rise to the Z2 to 1 form symmetry given by this equation here for the G group. And a general one form symmetry operator is generated by a product of poly X operators on faces of two cycles of the lattice cell, and edges dual to the two cycles on the dual lattice. Now the only symmetric bulk excitations are found by combinations of closed loop objects, and we refer to them as loop excitations. Both the primal and dual loop excitations have an energy cost proportional to their length and are thus confined. This confinement leads to the thermal stability of the model. Now let's move on to the boundary properties of the RBH model. To obtain degeneracy in the ground space, we must consider a lattice with boundaries. The allowable boundary Hamiltonians are dictated by the symmetry action on the boundary, which in turn is determined by the boundary geometry. So in addition to changing the ground speed degeneracy, the choice of the boundary Hamiltonian may allow for different types of excitations to condense on. Here by condense we mean that an excitation can be absorbed on the boundary or emitted from a boundary. So we refer to a boundary as primal condensing or dual condensing if any primal or dual loop excitation can be piecewise removed near the boundary using local symmetric operations. A schematic for a dual condensing boundary is shown in figure 6 over here. Now macroscopically, these types of boundaries can be thought of as analogous to the X and Z boundaries of the surface code that we've seen. Now let's take a look at an important boundary that is both primal and dual condensing, which is the toric code boundary. We consider a lattice with one boundary component and we terminate with the toric code boundary conditions. You can see it in figure 7 here. Namely, the cubic lattice is terminated on a smooth plane such that there are boundary volumes, boundary faces, boundary edges and boundary vertices, each having a lower number of instance cells compared to the bulk. Label the collection of all volumes, faces, edges and vertices by dou L. For this geometry, we consider Hamiltonians of the form H equals HL0 plus H dou L. A general boundary Hamiltonian can be written in terms of operators on the boundary algebra. So because of that, we must analyze the action of the one-form symmetry on the boundary algebra to infer how the boundary degrees of freedom transform under the symmetry. Now taking the boundary symmetry operators SV and SQ with V belonging to capital V intersection dou L, Q belonging to capital Q intersection dou L. For any E belonging to capital E intersection dou L, we have the following symmetry operator definitions. And from this we can write the action of the one-form symmetry in the ground space of H in terms of operators in the boundary algebra. Now define the following dress-toy code operators for each B and each F as follows: AV and BF as given in the equation. And such operators AV and BF are depicted in figure 7 over here. In figure 7b you can see the boundary terms AV bar and BF bar. Now it can be verified that the one-form symmetry acts as the following equation: SV equals AV bar and SQ equals BF bar for all V belonging to capital V intersection dou L and Q belonging to capital Q intersection dou L. And for all of the cases it acts as the identity. Thus we see that the SPD ordered bulk requires the boundary theory to be non-trivial. In order to respect the symmetry, any boundary Hamiltonian must commute with the dress-toy code operators, and therefore any trivial boundary Hamiltonian is ruled out. So now let's take a look at other types of boundaries that are of importance for construction of an SCQM. This is essential because we require certain condensation properties to ensure that all logical operators of the code can be implemented using sequences of local symmetric modes. And three such boundaries of interest are as follows: the primal boundary, which is primal but not dual condensing; the dual boundary, which is dual condensing but not primal condensing; and the sync boundary, which is both primal and dual condensing. And the Hamiltonians for all these boundaries are given by the single equation over here, which is H boundary equals minus sigma kf minus sigma ke. Kf and ke are the cluster terms that we saw before. Now let's move on to the cubic RBH code. We now use these various boundaries that we saw before to construct a code that is self-correcting under one-form symmetries called the cubic RBH model. So for the lattice, we consider a topology of a 3-ball. We consider cubic boundary conditions. That is, the lattice is a cubic lattice with dimensions d cross d cross d with 6 boundary facets as depicted in figure 9 over here. The bulk of the model is given by the usual RBH cluster Hamiltonian that we saw before, the HL0. While each of the 6 boundary facets we choose to have one of 4 different boundary conditions. Now the Hamiltonian decomposes into the bulk and boundary components. Again, the bulk is given by the RBH cluster Hamiltonian, whereas the boundary ones are given by the 3 types described in the previous section. That is the dual, primal, or the sync boundaries. Now let's look at the logical operators and code space for this RBH model, for this cubic RBH code. The total code Hamiltonian H dou L encodes one logical qubit with string logical operators x and z running between opposite pairs on the edges of the boundary face. In particular, we have x bar and z bar described by these following equations, where AD is a dual cycle on the boundary that runs between the two smooth edges. BP is a cycle on the boundary that runs between the two rough edges. And these logical operators are depicted in figure 10. Over here we can see the x running between the left and right smooth edges and z running between the top and bottom rough edges. Now let's look at the energy barrier. The symmetric energy barrier for logical fault in the cubic RBH model is lower bounded by this quantity here, d times delta gap by 2 minus r prime, where d is the lattice width and r is a constant. And we can see that this increases with system size exponentially. Hence, requirement for an SCQM is satisfied by the cubic RBH model. So now let's move on to the second example that is studied in the paper, which is the gauge color code in 3D. The gauge color code is an example of a topological subsystem code, which means in addition to local logical degrees of freedom, subsystem codes also contain redundant gauge degrees of freedom that are not used to encode information. A subsystem code is specified by subgroup G of the polygroup known as the gauge group. A stabilizer group S for the subsystem code can be defined by choosing any maximal subgroup of the center Z of the gauge group such that minus identity does not belong to S. Code space CS is defined as the mutual +1 eigenspace of all elements of S. The information that we want to code is only encoded into the subsystem of CS that is invariant under all gauge operators G belonging to the gauge group. Now the gauge color code lattice defined on lattices known as 3-colexes. In particular, a 3-colex is the result of gluing together 3 cells, polyhedra, such that each vertex is 4-valent and 4-colorable. By 4-valent, here we mean each vertex belongs to 4 edges, and 4-colorable meaning each polyhedral 3 cell can be given one of 4 colors, such that the neighboring 3 cells are differently colored. And we can choose these four colors to be labeled as I, B, G, and Y for red, blue, green, and yellow. Now we note that similar to the RPH model, the gauge color must have boundaries. The gauge color code must have boundaries in order to possess a non-trivial subspace. For concreteness, we choose these boundary conditions to be the tetrahedral boundary conditions. So the 3D gauge color code. For each vertex of the lattice tetrahedral called like C3, we place a cube. We have an X and Z gauge generator for each face of the lattice given by this equation here, where GXF and GZF are Pauli operators supported on the face F. The stabilizers of the code are given by the X and Z on the three cells of the lattice given by this equation here. SXQ and SZQ are the Pauli operators supported on three cells. Now with the aforementioned boundary conditions, the code encodes one logical qubit. The bare logical operators for this qubit can be taken similarly to the RBH model. We are therefore justified in viewing the logical information as being encoded on the boundary, as we would get with the 2D SAT model, which is encoded on the boundary of 3D SPT model. Now we can define an exactly solvable Hamiltonian by this equation, where GB is given by this set and KF denotes the color of face F. The commuting model HGB, here defined here, without any symmetry constraints, is easily shown to be disordered at any non-zero temperature because it's just a collection of uncoupled 2D color codes, that is 2D SET codes or symmetry-enriched topological codes. Now this Hamiltonian HGB has a Z22 one-form symmetry given by the stabilizer group S, which was described before. This one-form symmetry couples the bulk and boundary excitations, as was the case in the RBH model. Now the argument for the symmetric energy barrier to self-correction follows identically to that of the RBH model. That is, provided the temperature is sufficiently low, information can be stored for a time that goes exponentially with the system size. As a result, our stabilizer model, based on the 3D gauge color code, protected by Z22 one-form symmetry, provides another example of a self-correcting quantum memory. Alright, so to conclude, we saw that spin lattice models corresponding to 2D SET outer boundaries of thermally stable 3D SPT outer faces protected by soluble one-form symmetry can be SCQMs or self-correcting quantum memories. The key features of these one-form symmetric models are that the bulk excitations are string-like and confined, and the symmetry naturally couples the bulk and boundary excitations, which means the boundary excitations are confined as well. And we have presented two explicit examples of the 3D self-correcting quantum memories protected by one-form symmetries, namely the RBH model and the cubic RBH code, and the 3D gauge color code. The understanding and classification of such 3D models, however, remains largely unexplored. A key open question is how to construct more general families of models which emerge in higher form symmetries. Understanding of the SPT ordered phases and SCQMs in general will lead to vast developments in different areas, such as measurement-based quantum computing, topological quantum computing, quantum error correction, etc. So that's been it from me. Thank you for watching and have a great day.